Hello. Here we're going to take a relatively brief look at the last 2 billion years or so of the Grand Canyon's geologic history. Try to come to understand how these amazing landscapes came to be, how the various rock layers formed, and what that tells us about the history of the Earth. I'm going to be showing you a number of photographs of a very nice display at the Grand Canyon Geology Museum at Yavapai Point. It very nicely illustrates, kind of step by step, the important things that happen in the area to eventually form the Grand Canyon. Some of them are just diagrams and a little bit of text. Some of them have a nice three-dimensional block showing what the landscape may have looked like at that time. Let's start with the geologic map. Geologic map, this is of all of Arizona. These maps are very important tools for the geologists to try to unravel the Earth's history. They show us the present day configuration of rocks at the surface, and with this and other information we can work backwards in time to figure out what happened. So geologic maps like this one are color-coded, where rocks on the map are organized by a particular color. And if you are standing here, for example, near the Grand Canyon South Rim, you pick up one of these rocks, you can come over to the legend and figure out, based on the color, what its age is and the type of rock. Similarly, here's one that zooms in on the Grand Canyon area. Again, it's color-coded with the legend down here. This one also includes a very nice set of cross-sections in various places in the canyon, showing you how the rocks have been faulted and folded over time. I'm going to be utilizing this one quite a bit in the subsequent field trip stops. You're going to be seeing snapshots from this from a number of places. This one works slightly differently. It's interactive in that instead of showing you all of the legend of all the rock types, it only shows you the one that you're looking at. So if you hover your mouse, for example, over a spot there along the south rim, in the lower left-hand corner pops up a little window showing you the rock type and the corresponding symbol. All right, so here's the geologic timeline. This diagram very nicely puts in some time context of the various layers of the Grand Canyon. The most famous layers, the uppermost ones in the canyon, are of Paleozoic age, namely Cambrian and Devonian to the Permian. There's also some older layers. The Grand Canyon supergroup is here, and the older metamorphic and igneous rocks are down here. Those are both Precambrian. So the Precambrian corresponds to a very large chunk of Earth's history, as you can see over to the right. So to be a bit more precise, I'm going to be referring to the rocks in this time period. This is the Proterozoic. So the Grand Canyon supergroup and the metamorphic igneous rocks are in fact Proterozoic in age, and so that's how I'll be referring to them throughout this field trip. So let's start with a cross-section. This is a look or a schematic of the entire Grand Canyon with the oldest rocks, these Proterozoic Grand Canyon Metamorphic Suite, which includes some igneous rocks as well. The Grand Canyon Supergroup, also Proterozoic, and overlying all of that, the Paleozoic suite of sedimentary rocks. We're going to start at the oldest, the Proterozoic Metamorphic and igneous rocks, then move towards the supergroup, and then talk about the Paleozoic stuff here at the end. Just one note about this diagram, it is not to scale. For example, the supergroup rocks, this suite of mostly sedimentary rocks, is over 12,000 feet thick, which is more than twice the thickness of the Paleozoic rocks. So there's a whole lot more supergroup rock down there than what this diagram shows. And up close and personal, it's all of the stuff down here. Close look, composed of black or nearly black rock, such as here or here. This is the metamorphic component, schist and gneiss, depending on where you are. And inside of there is this pink stuff, which is granitic igneous intrusions. They're slightly younger, but by and large, they're the big picture, they're the same age. They all formed between about 1.85 and 1.65 billion years ago. So how did they form? So let's go back 1.8 billion years ago and look at the continent which will eventually become North America. We call it Laurentia. It wasn't the same size, shape, or even location as present-day North America. It's quite a bit different. So it was in a phase of growth at this time. Continents grow by way of accretion, where we have subducting plates. This one subducting to the right has an island arc on it. That island arc is not dense enough to subduct, so eventually when it gets over to the trench, these islands essentially get scraped off and get pasted on the side of the continent, thereby growing it. This was occurring quite a bit on the southeastern margin of Laurentia during this time. Plates were subducting to the northwest in this view, and there were significant accretions to Laurentia. It grew in big chunks. The Mazatzal province, this green, the Yavapai province, and this purple, the Mojave province, represent major accretions to Laurentia via this subduction process. In particular, the rocks that of the Vishnu basement, which formed in the Grand Canyon area here, formed by way of metamorphism of the intervening sediments and volcanic material that accumulated in the ocean basin in between the island arc and North America, and this material was compressed and highly metamorphosed and pasted onto the edge of North America to make those Vishnu basement, the metamorphic and igneous rocks. Here's a diagram representing how that occurred. So here we have the accumulation of sediment, fine-grained sediment, and volcanic deposits such as ash deposits from this volcanic arc. And this stuff accumulated here, it was compressed in this diagram left-right, and folded and metamorphosed and faulted, etc., to make those metamorphic rocks here, down at about 25 kilometers depth. This is what it looks like a bit closer. Everything beneath this red line is this Proterozoic age. The dark stuff is the schist and gneiss, collectively referred to as the Vishnu schist. And the kind of pink stuff is a granitic composition, often referred to as the Zoroaster granite. Up close again, this is what it looks like. These rocks are highly foliated, highly metamorphosed and foliated. And in big picture, it's near vertical foliation. You can kind of see the lines in the rocks here. This is where the minerals are all lined up more or less close to vertical. And if you get really up close, you can really see how this stuff was twisted and contorted during metamorphism as it was squeezed, as it was forming. Following the formation of this rock, this area was relatively quiet, tectonically quiet. And so the growth of Laurentia was occurring, but occurring farther away. And so this part of the continent was relatively quiet. And in fact, there was a long period of uplift and erosion until about 1.2 billion years ago. There was a period of 400 to 500 million years of uplift and erosion. And this is what the landscape may have looked like then. Relatively flat, maybe some river channels, underlain by this metamorphic rock, which was formed previously. This is what it might look like. You have to use your imagination a little bit. So here's this erosional surface. Everything below here is the Proterozoic rock. All of this isn't there yet. So imagine a flat surface, sort of as depicted here, underlain by this igneous and metamorphic rock below. This period is also important in that it represents the start of the growth of a supercontinent called Rodinia. It's a common process on Earth for continents to move together, form a supercontinent, and later break apart. Most recently, this happened with the supercontinent of Pangaea, but if you go back farther in time to about 1.2 billion years ago, we had the growth of the supercontinent Rodinia, and this is what it may have looked like, where we have Laurentia, and off to the west, pieces of continent which will eventually become Siberia, Australia, and Antarctica. The breakup of Rodinia, when this continent splits apart, will become very important here shortly. Following the long period of uplift and erosion of this Vishnu basement rock, we had a long period of deposition, of a sedimentary deposition. Here's the Grand Canyon area in Laurentia. There was significant tectonic activity here, but we were far enough away that this area was relatively quiet and really acted as a big basin to collect sediment over time. In fact, there's some evidence that there may have been even some subsidence in order to accumulate significant sediments. So during this 1.2 billion years to about 750 million years ago, we accumulated the Grand Canyon supergroup rocks, which are about 12,000 feet thick of mostly sedimentary rock, with the Bass Formation on the lowest level, the lowest layer, which is limestone, indicating that these rocks were accumulated here at or near sea level, and the uppermost layer, the Chuar group, which is another fine grain, near marine or shallow marine sedimentary rock. So accumulation of the Grand Canyon supergroup between about 1.2 billion years and 750 million years ago. All right, here's what the supergroup looked like in the eastern part of the canyon. Here is the boundary between the Vishnu basement rocks and the supergroup rocks which overlie it. You have to use your imagination a little bit here because everything above this red line that I'm drawing isn't there yet. Similarly, in the image below, all of this here, all of these rocks are supergroup, and everything above this red line, which I'm sketching in, isn't there yet. The supergroup rocks are all tilted off to the right. We'll get to the reason why here shortly. Following the formation of Rodinia, deposition of the supergroup rocks, the supercontinent of Rodinia began to break apart around 750 million years ago, where the continents on the western margin of Rodinia, that is, those will eventually become Siberia, Australia, and Antarctica, began to move away from Laurentia to the west, which placed this part of western part of Laurentia, where Grand Canyon will eventually form under extension. So here we have the supergroup deposited on the Vishnu basement rocks here, and when you take rocks and you stretch them, in this case left-right, you form normal faults. So here's an example of a normal fault where the rocks on the left are going to move down relative to the right. So here's how that may have looked afterwards. There were a number of normal faults that formed, but here's just an example of how you take, this is the before, stretch these rocks move down on the left and tilt, and here's the resulting distribution of the rocks following this faulting event. There was extensive stretching and faulting throughout this part of Laurentia. One of the best examples of this in really anywhere is called the Butte Fault. Okay, notice this contrast between these dark rocks here. This is a Cardenas basalt, a layer of lava which formed kind of in the middle of the Grand Canyon supergroup, adjacent to this lighter colored red rock called the Docks Formation. We have different rock types of different ages adjacent to one another because they are adjacent to this guy here, which is the Butte Fault. This is a really important structure in the Grand Canyon, and you're going to be hearing about it a lot in this short geology overview and in many of the field trip stops to come. So the Butte Fault is essentially this structure here, where the rocks on the left-hand side move down relative to those on the right during the breakup of Rodinia, roughly 750 million years ago. If we go around to the north rim, we can see a really nice outcrop of the Butte Fault and the effect that it had on the rocks there. During extension and faulting, some folding also occurred, especially the uppermost layers of the supergroup rock, which were forming during this extensional phase, and they actually got folded in a very gentle syncline here, which we can see here. It's called the Chuar syncline because it formed in the Chuar sediments, and it's a very gentle syncline, but it's pretty obvious from many points along both the north and the south rim. Here's a bit more up-close look at the Chuar syncline, where you can see these sediments have this very gentle U-shape to them. And this occurred during the extensional phase, roughly 750 million years ago. Following the period of extension, faulting, tilting, and folding of the supergroup rocks, we had a roughly 200 million year period of erosion, which removed most of those supergroup rocks and left a relatively flat surface. There are some erosional remnants of the supergroups left, but by and large, we have a wedge of supergroup rocks in the eastern part of the canyon, and they've, for the most part, been removed from virtually everywhere else within the canyon. Following the erosion erosion and removal of the Grand Canyon supergroup rocks, this part of North America returned to an environment of deposition, namely subsidence of the continent as a result of the breakup and extension of Rodinia, produced a prime place to deposit marine or near marine sediments, such as depicted here, sediments which formed on the seafloor, such as shale or limestone, or those that can form near the continental edge, such as sandstone. This sequence of Paleozoic rocks very nicely records the environmental history of the area. Probably the best example, most famous example, is the transition from the Tapeats sandstone, which was the first layer of the Paleozoic rocks to form. It represents beach sands. Above that we have Bright Angel shale, which forms on the seafloor. So from the period of Tapeats forming to the Bright Angel, we had a period of sea level rise. And above that, we have a layer of the Moab limestone, which represents an even deeper water marine sedimentary deposit, and so more sea level rise. There are other sequences just like this recorded throughout the Paleozoic sequence, but this is the classic one of a marine transgression or sea level rise, when we go from sediments that formed above sea level to those that formed well below. So in the eastern part of the canyon, the Paleozoic sequence, which is everything above this red line here, formed on top of the tilted supergroup rocks. In the western part of the canyon, everything above this red line here, which is the Great Unconformity. All of this is the Paleozoic sequence, which was formed directly on the Vishnu basement rocks. Here's some up-close looks at some of the Paleozoic sequence. We're standing approximately on the Bright Angel shale and Moab limestone contact. So here is the Bright Angel shale. It's fairly vegetated, hard to see. Above that is the Moab limestone, this kind of yellow and green layer. Above that is the red wall limestone here. I show you this particular image because of this waterfall. This is Roaring Springs. This is where all of the water at the Grand Canyon, both north and south rim, comes from. It doesn't come from the river. It comes from the spring well down in the canyon, and it's pumped up to the rims for people to access. Here's a look at the uppermost section of the Paleozoic sequence. This is looking north along the Bright Angel Trail. Here we have the red wall limestone. Above that, above this line between here and here, is the Supai group, which is a layer of shales and sandstones. Above that is the Hermit Shale, which we can't really see at this angle. Above that, the kind of white layer, is the Coconino Sandstone. Above that, the Toroweap Formation, which is kind of a sandy limestone. And above that, the topmost layer, is the Kaibab Limestone. Now, on top of the Paleozoic sequence of rocks, there used to be another 5,000 or so feet of Mesozoic rocks, but they were subsequently removed. And so how and when and why they formed, and how and when and why they were eroded away, is an interesting story, but for the sake of time, we'll have to save that for another day. The Paleozoic sequence of rocks are a sequence of rocks deposited at or near sea level, shales, limestones, and sandstones. However, they now sit at many thousands of feet in elevation, as much as 8,000 feet in elevation along the north rim. So how did those rocks which formed at sea level get to above 8,000 feet? So following their deposition and the Mesozoic and removal of those Mesozoic rocks, as I mentioned a moment ago, the western U.S. underwent a period of extensive compression between about 70 and 40 million years ago. This is the period during which the Rocky Mountains were formed, and it's the period in which the Kaibab Plateau was formed when it was uplifted. So what we have is rocks that are under compression, roughly east-west. We form reverse faults. So here's the before on the left-hand side, and here's a reverse fault, which eventually accommodates that compression. And the rocks on the left have been moved up relative to those on the right. You may be familiar with this diagram because this structure here is our friend the Butte Fault. It started out as a normal fault during the Proterozoic, but it was reactivated as a reverse fault during this period of compression, during what's called the Laramide orogeny. We can see evidence of this uplift very clearly from a few spots along the eastern part of the North Rim. Here we have flat-lying sedimentary rocks, the Paleozoic sequence, off to our left, and they dip very gently and then are flat-lying again off to our right. Okay. What we're seeing is kind of this section of this diagram. The uplift and tilting in this diagram is exaggerated quite a bit, but nonetheless you get the idea. We have relatively flat-lying rocks here, they're tilted off to our right, and then flat-lying again, just like we have here. This is a picture from the East Rim viewpoint. And here's another from Marble Point. We have flat-lying sedimentary rocks. They're folded. This is the East Kaibab monocline, and then they're flat-lying off to the right. We're just flat-lying, folded, and then flat-lying off to our right. And this occurred, this uplift and this folding and faulting occurred roughly 70 to 40 million years ago during the Laramide orogeny. There's also good evidence for this from the North Rim, back to our friend the Butte Fault. So here we're on the North Rim looking to the southeast. What I want to point your eye to is this kind of white or grayish sequence of rocks here along this line. This is the outcrop of the Butte Fault, okay? And so given the view that we have during the compressional phase, the rocks on our right, these were moved to the left and upwards along this fault structure. So what we're seeing here is these rocks moving upwards relative to the Butte Fault. And if we zoom in and take a close look at the Butte Fault here, this is what you can see. So here again, here's the trace of the Butte Fault, and these rocks are being pushed to our left and upright. What you can see very clearly is these rocks, these are the Supai group rocks, which were deformed. As these rocks are moved up and to our left, the rocks on the left kind of get drug along and folded upwards as a result. And you'll see some really nice images of this in the North Rim and South Rim field trip stops. Following the compressional phase in the western U.S., which resulted in uplift of the Kaibab Plateau, due to changes along the western boundary of western North America, changes in the plate tectonic situation there, big sections of the western U.S. have undergone extension, starting at about 30 million years ago in the westernmost part, sort of in this area, and about 17 million years ago it started in the Grand Canyon area. There's a region of the western U.S. called the Basin and Range Province, which I'm outlining here. It extends down into Mexico as well, where roughly east-west extension has occurred quite pervasively, and that's produced this pattern of mountain range adjacent to a basin, adjacent to a mountain, adjacent to a basin, etc. In fact, so much extension has occurred here that the east-west distance between San Francisco and Salt Lake City has approximately doubled over the last 30 million years. This type of extension, this east-west stretching of the crust, has occurred in the Grand Canyon area, although to a lesser degree, although it does play an important role in understanding the history of the Grand Canyon. So, for example, back to our friend the Butte Fault. Here's the Butte Fault, an extensional structure formed during the Proterozoic, reactivated as a reverse fault here during the Laramide, during the 70 to 40 million year period of compression, and then during this basin and range period from 17 million years to present, it's been reactivated again as a normal fault. Another example is here. We're standing in the Bright Angel Fault Zone, which extends roughly in this direction. And notice the difference in elevation between the red wall limestone on the left and the red wall limestone on the right. Here's the top of the red wall on the left, and here's the top of the red wall on the right. The left side has been uplifted by motion on the Bright Angel Fault as a normal fault during this period of extension, which has occurred in the Grand Canyon area from about 17 million years ago to present. Okay, finally, we need to talk about the canyon itself. We've finished our discussion of the rocks, how the rock layers formed, when, and why they are where they are at present. But what about the canyon? What about the air where the rocks used to be? The canyon has been carved by the Colorado River and possibly its ancestors, that is, previous rivers which flowed in a similar place and possibly in the same or even different directions. and mass wasting processes, landslides, which take chunks of the canyon and drop it down towards the river, and the river carries it away. It's certainly a process of the river playing a role in erosion and landslides and such as well. The real question is, when did that occur? Is the canyon formed relatively recently? A lot of people think that the Grand Canyon may be as young as only 6 million years ago, although there's evidence as well that parts or maybe all of the canyon are significantly older, more like 60 million years old. There's a significant debate right now whether the canyon is, quote, old, formed roughly 60 million years ago, or it's quite young, formed only 6 million years ago. And in fact, there's evidence to suggest that both of those are true. Perhaps parts of the canyon formed 60 million years ago, and parts of it only 6 million years ago by the river that we now call the Colorado. In terms of understanding Grand Canyon geology, this is probably the area which is least understood. In the eastern part of the canyon, where the river flows through the relatively soft sediments of the Grand Canyon supergroup, it takes a fairly broad and meandering kind of lazy path through these rocks because they're easily eroded. In the western part of the canyon, where it flows through the Vishnu basement rocks, it forms a deep and relatively narrow canyon because those rocks are much more resistant to erosion. All right, there we are. There is your fairly brief introduction to the geologic history of the Grand Canyon. Feel free to refer to this while you're walking through the field trip stops. And thanks for listening. I'll see you soon.